Guys, welcome to our channel of Science and Mathematics. Today we're going to look at a different aspect under the gas laws, and this is the concept of diffusion and Grams law. Now we find that one of the properties of gases is that they can be able to diffuse or move from regions of high to a low concentration, and the specific illustrations that I've given on the board for 1, 2, 3 is going to assist us have a way in which we can be able to quantify or find a relationship in which we can be able to describe this aspect of diffusion of gases. Now, this is summarized under the concept of Grams law, and we're going to see that one shortly using the above illustration. So thank you and welcome. So today's topic of discussion is diffusion and Grams law, and this basically deals with the characteristic ways in which different gases, of course, can be able to diffuse through medium using their particular properties, which we're going to see later. Now, I've given 3 illustrations on the board for the first one, and the second and the third one. Now, basically, we're going to use the first and the second one to do a comparison of one of the aspects of this Grams law, that is diffusion. So in the first setup, I have water that is in a container, and there's a crystal of potassium permanganate that has been put in that specific water. Now, over time, we're going to see that there's a transition that is going to occur, and there is going to be coloration of this specific water that is here. Now, we can explain that one in a sense that a crystal of potassium permanganate that has got a purple color, this purple color spreads uniformly in this water over a period of time. And this particular concept now we are going to describe it in a term. So we just refer this one, reserve this one for that. Now in the second setup we have this is a combustion tube that we are having with a setup of which is secured on both sides. So here we have a cotton wool that is soaked in ammonia, and at the one end, let's refer to this one as end AB. So at end A we have got a cotton wool that is soaked in ammonia, and the other end we have a wet red litmus paper. So after some time we will find that at one end from this the red litmus paper will change to blue, and that observation, of course, we are going to compound it with this first one in order to try and find out which characteristic behavior or a specific behavior for these liquids and gases that is being displayed here. So for illustration, we're going also to see that we can be able to allocate a specific term for the first and second setup respectively. Now for the first setup, this is a spreading of particles in a liquid, and the second one is the spreading of particles in a gas. So in this case, we can explain in this sense that, of course, this particular potassium permanganate crystal does not spread as a whole, but in form of particles that emanate from these particular crystals and spread uniformly to form this purple solution. Of course, it's not purple, but it's an illustration. This potassium permanganate is a crystal that forms a purple solution in water. That's why I'm using the term purple. So in this case, for the second setup, you find that there will be some particles of ammonia that spread from this gas, and whenever they come across this wet litmus paper, they are going to form a base, which is a hydroxide, of course. But this hydroxide, since it's basic, is going to change red litmus paper to blue. So the concept we're trying to talk about here is this aspect of phenomena of this potassium permanganate and the gas spreading out through a specific medium. Now we will assume that for these particles to be enabled to spread, they possess kinetic energy, and we're going to see later that this of course assists them in trying to spread out. Now one aspect of these two specific setup that we're going to see is that if we set time for this specific setups to go to completion, we'll find that for the first one, this is let me refer to this as T1. T1 will be smaller than T2 from the specific experiments or hypothetical examples that we might be able to do, of course, to do a practice of 1 or 2. But basically T1 is going to be shorter than T1 is going to be longer than T2, implying that T2 takes a shorter time in order to spread out. So basically, this one has the thing being a liquid and this one being a gases. We're going to see that gases display a shorter time in spreading compared to liquids. Now in our third setup, we have a setup of a combustion tube that has got cotton that has been soaked in conch hydrochloric acid, and this is a cotton that has been soaked in conch ammonia. Now I've referred to both X as A and B, and in this case we're going to see that this particular setup is going to assist us in trying to find some of the aspects we can be able to compare in trying to look at the diffusion of gases from this specific aspect. Now this and this one are the same, only that this particular end, instead of a litmus paper, we have ammonia gas. So when these particles will start spreading from this end, and of course the others particles for the ammonium will spread from this other end. From the stoichiometry of chemical equations, we know that if they meet at a particular point, after some time at this specific point, maybe let's refer to that one or that specific point at point C, the particles that are spreading of this specific ammonia and HCl meet at this specific point D, maybe some distance D1 from A and some distance D2 from B. They're going to form a white dense cloud of ammonium chloride. Now that's from reactions, that's a stoichiometry. We're going to see that this is going to form ammonium chloride. This of course is going to be seen as a dense cloud that is going to be formed at that specific point. Now the distance D1 and D2 is going to assist us to do an analysis and find out with respect to time what is the rate of diffusion of this substance A or B or gas A or B using that specific setup. Now therefore the relationship that is given by the division of D1 and D2 is going to be expressed using the Gram's law, which is going to compare the rate of diffusion of different gases and therefore maybe give it in different quantities, which we're going to see. Now generally we can say that the spreading out of particles of matter from a region of high concentration through a medium can be referred to as a diffusion. So we can write this one here. So the term diffusion refers to spreading out of particles of matter from a region of a high concentration to a region of low concentration through a medium. So basically whatever we have been trying to illustrate in these three setups is the concept of diffusion, and the Gram's law comes in trying to quantify some of the aspects that you can see that the distance which basically over time will give us the rates of diffusion of these specific gases. Now different gases have different rates of diffusion, as we're going to see that there are some of the other aspects that we're going to compare in order to quantify this relationship, as I already said. Now suppose we give an example and say that the distance D1 and D2 can be measured. We can be able to give this relationship for the rate of diffusion if the distance D1 and D2 are measured over time. So suppose I say that the distance D1, which is basically SC, that gas moved 8 centimeters in 5 minutes. So basically we're going to compare the two distances using the same time, and the distance BC, the gas moved 12, so just hypothetical examples, in 5 minutes. Therefore the rate of diffusion can be able to be compared now that we have been given the distance over time. So therefore for ammonia, which is on the other end, which is having the distance of 12, so the rate of diffusion is going to be 12 centimeters in 5 minutes, which is going to give us 2.4 centimeters per minute. So this is the rate of diffusion of ammonia. And then for HCl, we're going to see that it's take 8 minutes in 5 8 centimeters in 5 minutes. Therefore, this is going to be 1.6 centimeters per minute. So that's its rate of diffusion for that. Now we can have a relative rate of diffusion, which is probably particularly a comparison between the rate of diffusion of these two gases, whereby we have the rate of diffusion of ammonia. I'm going to use the capital R for rate. So this rate for ammonia over rate for HCl can give us the relative rate of diffusion for the two gases. Therefore, we are going to have this one as 2.4 centimeters per minute divided by 1.6 centimeters per minute, which is going to give us a ratio of 1.5. This basically implies that ammonia diffuses 1.5 times faster than HCl gas, and this of course relationship is going to be given using Graham's law of diffusion. Now the Graham's law of diffusion summarizes this behavior, and it states that under the same conditions of temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density. Now we're going to give, as we have already done for others, the mathematical implication of this Graham's law, so that it can be able to assist us in interpreting these different aspects for diffusion of gases. So now let's look at this, of course, in the form of a mathematical expression. So we have said that Graham's law states that under the same conditions of temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density. So we can give this one as the rate is inversely proportional to the square root of its density. So this is for a specific gas. So therefore, as we have done for others, we find that the rate represented by R is equals to a constant over the density. And in this case, if we have maybe a gas A that is undergoing diffusion, therefore we are going to have the rate of A over the inverse of A. So similarly, if we have a gas B that is undergoing diffusion, therefore it will be a constant over the root of B. So bearing in mind that for these two constants we can have a relationship between gas A and B, which is being illustrated as the rate of division of A, density of A is equals to the rate of division of B, density of B. Or this one can be rewritten as the rate of division of A over the rate of division of B, which is a relative rate of division, is equivalent to the root of division, density of B over density of A. So basically, since the density is directly proportional to molecular mass, so we can do a comparison between this density and the molecular mass for specific gases. This is molecular mass for specific gases, and therefore have a different version of representation of this specific law using the relative molecular mass. Since, as we have said, density is directly proportional to the molecular mass, and therefore this law can be given as rate of A over rate of B is equals the root of the molecular mass of B over molecular mass of A as such. So we can also look at the other aspects, which are maybe a comparison with either the rate or the density, as we have done a comparison for density and relative molecular mass. And we're going to see that rate is also inversely proportional to time. And this case it refers to the time of diffusion. So we're going to have a relationship whereby rate is inversely proportional to time. Therefore, we can have a mathematical representation for that, whereby we have the rate of division of a gas A is equals to a constant divided by the time of division of a gas A. So that one can be represented as such, which basically we can be able to give as TA. So therefore we can have an expression which also gives us a relationship between time and rate, which can be expressed as such. So therefore, combining the aspect of density, mass, and rate, we can be able to have a general representation for this specific relationship for Graham's law, which can be written as the one I'm going to just put on the board, whereby we have said that the rate of A over rate of B can be able to be, it just can be illustrated as density of B over density of A, which can be given as the molecular mass of B over molecular mass of A. And of course, we have said the time for B over the time for A can be given as the density of B over density of A, which can be given as the mass of B over mass of A. So this is a relationship that exists between the masses of the densities and the time of diffusion for specific gases. And we can be able to use this relationship in order to find out maybe a a molecular mass of a specific gas, its density, and maybe the rate of diffusion of this law. So this basically encompasses the concept of diffusion and Graham's law, and we're going to illustrate this one using a specific example on the board. So I'm just going to do away with this so that we can look at a sample question and try to apply what we have discussed and find out a solution for that. So as usual, I'm just going to read through the question so that we can be able to extract the information and try to find the relationship, the suitable relationship that we have discussed that we can be able to use in order to find a solution. So a given volume of nitrogen gas requires 68.3 seconds to diffuse through a tiny hole in a chamber. Under the same conditions, another unknown gas requires 85.6 seconds for the same volume to diffuse. What is the molecular mass of this gas? So basically from the question we are being told that a given volume of a nitrogen gas requires 68.3 seconds to diffuse through a tiny hole in a chamber. Under the same conditions, another gas requires 85.6 seconds for the same volume to diffuse. What's the molecular mass of the gas? So basically, we're being asked the relationship between the molecular mass of gases in comparison with the time. And we've given an equation that it can be able to be represented using the time and the molecular mass of compounds in this different version of our Graham's law. So what we know is that maybe we can check on this. The nitrogen is an atomic gas that can be represented for the relative formula, the molecular mass of 28 grams per mole. And this other gas, maybe that we are going to refer to as the gas X, we do not know its molecular mass in grams per mole, and therefore this is what we are being asked to find. What's the molecular mass of the gas? Bearing in mind that we have been given the time for diffusion of the two. Therefore, the relationship that we are going to use for this particular set of a problem is that the time taken for nitrogen over the time taken for this specific gas X can be represented as the root of the molecular mass of nitrogen divided by the molecular mass of gas X. Therefore, for us to find the molecular mass of gas X, we're going to make this part of the formula, the subject of the formula, and we are going to use this one. So basically, trying to use this relationship, we're going to see that the time taken for ammonia and the time taken for X is the same as the root of the molecular mass of ammonia and the molecular mass of X. Now, making this one the subject of the formula, we're going to basically square the both sides in order to get out this root sign. So therefore, this is going to give us this, whereby we do a substitution for the the formula mass, the molecular mass for ammonia, and then over the molecular mass for X. The square of this is going to give us this figure. So therefore, we're going to make this one the subject of the formula and do a substitution by by just doing a division of this one in order to find 43.98, which is basically going to give us the the molecular formula for X being 44 grams per mole. So in looking at this, the rate of diffusion of that we have been seeing that exists between density, molecular masses, the time and the rate of diffusion can be able to assist us in solving problems of the same kind. So that is it for today. Thank you. Bye. God bless.